Hello, and welcome to the Farrat Industrial CPD Module 2, Noise and Vibration Effects of Impact Machinery. This course is worth 20 credits. Let's get started. In this module, we will examine the effects of impact machinery on a production facility, and will explore some of the solutions used to properly isolate these effects. This module is formed as a case analysis, which will use in situ measurements to illustrate the root problem and offer practical solutions. First, we will define what impact machinery is. Secondly, we will present practical techniques to isolate this type of machinery and demonstrate what a typical Farrat anti-vibration system looks like. Then, we will explore ways to measure vibrations generated by impact machinery and show how this procedure has been used to undertake vibration surveys on similar impact machines from different factories. Finally, practical examples will be presented to illustrate the potential effects vibration can have on the overall productivity of the machines and on nearby sensitive machinery. To begin, here's an overview of what impact machinery is. Impact machinery is described as machinery that generates a force or a shock over a short period of time. External excitation acting on the structure can take many forms. The most common in the industrial world is the harmonic excitation that can be found when rotating movements take place. The second is shock, which occurs when percussion machines are used, such as impact machinery. Impact machinery generates impact. In mechanics, an impact is a high force or shock applied over a short period of time where two or more bodies collide. This type of force is typically generated by industrial machines such as forges or presses. These machines involve a manufacturing process shaping metal using localized compressive forces. The blows are delivered with a hammer or a die that change the shape of a workpiece by the application of important pressure. The shock produced can alter the proper functioning of the installation, systems and components, eventually reducing the machine productivity, damaging the building and generating waves and noises that propagate into the environment. They can affect the foundations of sensitive facilities and equipment and create discomfort or risk to the health and safety of workers and occupants of nearby buildings. Considering these damaging effects, it is therefore necessary to minimize the transmission of the shock forces and reduce the vibration level to the surrounding environment. This is where Farrat's expertise plays a critical role in the isolation of this type of machinery, designing and supplying bespoke anti-vibration systems. The first thing that comes to mind is to use resilient elements that will act as isolators. According to the ISO 2017-1 standard, isolators are flexible elements or systems used between an equipment and its supporting structure to attenuate the transmission of shock or vibration from the equipment to the structure. The isolator selection is done based on different factors such as the mass and speed of the machine, the level of isolation required, and any other aspect detailed in the first module, Isolation of Impact Machinery. What is usually encouraged in these types of applications is to add mass to the system. For this, a concrete inertia block is poured on top of the isolators so that they can achieve a certain level of compression and improve their performance in terms of shock absorption. The inertia block also provides more stability to the structure and reduces the rocking of the machine as a result of increased stiffness and lower center of gravity, thus maintaining alignment during changes in static and dynamic loads. The image on screen shows a typical industrial machine installed on an isolated foundation, made of an inertia block supported by isolators. This photo presents how a typical Farrat anti-vibration system looks like before the concrete foundation is poured within the pit. Cork composite strips are used on top of the side walls to add lateral stiffness and prevent rocking of the foundation and increase its stability. Void former is also used to support these strips on the walls and ensure a flat surface on the base to distribute equally the loads from the inertia block and the machine onto the elastomeric rubber pads, which also absorb shock and produce the machine to the isolated system. As part of Farrat's research programme, vibration surveys were undertaken in different factories to determine the performance of anti-vibration systems applied on industrial impact machinery. The image on screen shows how the vibration measurements were taken to diagnose the level of vibration before trying to take corrective actions. The machines measured in this scenario were copper presses, which are used to produce aluminium cans. In order to produce beverage cans out of rolls of aluminium sheeting, copper presses are the first machines in the process and perform two operations. Firstly, they punch out simple discs and form them into cylindrical cups. These actions generate vertical excitations that can be considered as shocks, repeated at frequencies determined by the speed of the machine. This type of press is connected to its foundation by resilient mounts, offering a soft connection. The inertia block placed below is supported by isolators and therefore isolated from the rest of the factory. In order to record vibration generated by the operating machines, accelerometers were used. An accelerometer is a transducer that measures the vibration or acceleration of motion of a structure. The force caused by vibration or a change in motion causes the mass to squeeze the piezoelectric material, which produces an electrical charge that is proportional to the force exerted upon it. The electrical signal is then transferred to a data acquisition card connected to a laptop that records and processes the data. As transducers must be attached to the surfaces of interest, in our comparison study, accelerometers have been attached to the 4 feet of the presses, the 4 corners of the isolated foundations, and the surrounding factory floors. This allowed a detailed analysis presenting how vibrations propagate across the entire system. From each of the various measurements performed across the 3 factories, you can see the following interesting results. The first chart presents the vertical acceleration measured on the feet of 4 different presses from 3 different factories. Factory 1 uses a DAC 150, which is a model of a press weighing around 40 tons. This machine was running at a speed of 156 RPM during the measurements. Factory 2 uses 2 models of presses, the same DAC 150 running at 115 RPM and a DAC 165 operating at a speed of 130 RPM. This last model is heavier with a weight of 60 tons and presents a vertical balancing system with counterweights supposed to reduce vibrations generated. Finally, Factory 3 uses a DAC 165 and it was measured at 2 different cadences, 158 and 225 RPM. The second chart shows the vibration levels recorded on the isolated foundations supporting those same machines in dark blue and on the surrounding factory floors in lighter blue. Let's analyse the obtained results. Factory 1 shows a vibration level measured at the feet of the machine very typical for a copper press, with an acceleration of almost 8 miles per second squared. However, no reduction can be observed from the inertia block supporting the press to the factory floor. This can be explained by the isolation system supplied by one of our competitors, which might have gone for a wrong design or product. Some bridging connections have also been observed, with one column in particular rigidly bolted to both the inertia block and the factory floor, helping vibration generated transferred around. This specific example will be developed in the next screen, showing how the poor isolation performance has affected a sensitive machine positioned nearby within the factory. Factory 2 presents 2 models of presses. Although the DAC 165 is 20 tons heavier than the DAC 150 and was running at a higher speed, they both present similar levels of accelerations, highlighting the efficiency of the DAC 165 balancing system. This time we can observe an important reduction of the vibration from both inertia blocks to the surrounding factory floor, proving the efficiency of the Farrat isolation system used for both foundations and achieving an overall reduction percentage of 99% from the machine feet to the floor. It is also interesting to notice that although the DAC 165 was running faster than the DAC 150, the accelerations recorded on its foundation and surrounding floor were lower than the DAC 150s. This demonstrates the remarkable properties of Farrat elastomeric pads, more performant when subject to faster machine speed. Factory 3 has got a DAC 165 press, which has been measured at a speed of 158 and 225 RPM. This increase of 41% in machine cadence results in a vibration increase of 44% in terms of vertical acceleration measured at the feet of the machine. This tends to show the linear relation between the machine's speed and its internal level of vibration generated. The increase of vibration at faster speed is also reflected on the foundation. However, the acceleration measured on the surrounding factory floor is similar for both speeds, and the overall percentage of vibration reduction is still 99%. This result demonstrates that the pads used under the inertia block can keep a very low level of vibration transmission, even when subject to higher level of energy, once again highlighting the unique mechanical behavior of Farrat rubber products. Another real-world case study can also be presented to highlight the performance of Farrat isolated foundation designs. In this instance, a cannon factory was having issues with a copper press, generating excessive vibrations that could be perceived by neighbouring buildings that were placed at a distance of 70 metres from the machine. A study performed by a consultancy specialising in vibrations and structural dynamics concluded that in order for this press to be properly isolated, a natural frequency of 1.25 Hz should be achieved by the isolation system. Based on this recommendation, the factory went for spring elements and visco dampers as shown in the photo, supplied by one of our competitors. It was reported that the surrounding buildings stopped perceiving vibrations generated by the machine after installation of the product. However, at the same time, it was also observed that the springs, together with the foundation and machine installed with them, started to present unexpected high movement. As a result, premature wear and increased spoilage were caused, reducing the overall productivity of the plant. Farrat was asked to provide a solution that would reduce the excessive movement of the press while maintaining a quiet environment for the neighbouring buildings. So the challenge was to stiffen the overall system while preventing excessive vibrations being transmitted around. In order to solve both parts of the equation, the engineering team worked on bespoke bearings made of a steel base and 2 layers of natural rubber as presented in the picture. A vibration survey has been carried out to measure vibration before and after replacement of the spring packs to assess the efficiency of the offered solution. The main result of this survey is presented in this plot, showing the vertical accelerations measured before replacement with the blue curves and after installation of Farrat isolation system with the orange curves. Vibrations measured at the feet of the machine are shown on top, on the inertia block in the middle, and on the surrounding factory floor at the bottom. A vibration reduction definitely appears on each part of the system. It is particularly clear at the operational speed of the press, slightly below 2 Hz. This is the frequency of interest since it is where the machine as a whole is likely to be moving and rocking. These are the vibrations that can be perceived and impact that the process quality has. It has been noted that these results were observed at all measured operational machine speeds between 110 and 170 RPM. These results demonstrate that the client's requirements have been met. The Farrat isolation solution has significantly lowered the movements of the machine whilst maintaining a quiet environment for the neighbouring buildings. This proves the efficiency of Farrat rubber isolation systems for this type of application, where bespoke design solutions are needed to solve complex engineering challenges. On the other hand, springs with visco dampers have proven unsuitable because of their very low natural frequency, dangerously close to the disturbing frequencies generated by the presses and increasing the risk of facing resonance issues. Now that we have seen the impact of vibration from poorly isolated presses, Let's focus on one particular example from Factory 1, which highlights one of the potential consequences that excessive vibration transmission can create. A direct laser exposure system using a direct laser engraving method is located in an office close to the production lines of Factory 1 and is 30 meters away from the press described previously. This machine is used to produce the masks which are needed to decorate the various types of cans produced within this factory, and requires a very high level of precision and stability to operate. It was reported by the line manager that this precision machine was subjected to excessive vibrations, altering its process quality. As a reminder, this is the chart presenting the vertical acceleration measured on the inertia block and the surrounding factory floor, showing the poor performance of the isolated foundation supporting the press. In order to determine the influence of the press, we have measured the vibrations on the printer in 3 different directions whilst the machine was on and off. The results are presented in this plot for X on top, Y in the middle, and Z at the bottom directions. The orange curves were obtained when the press was off, while the blue curves were obtained with the machine running at its normal operational speed. The first few peaks, all located below 20 Hz, were generated by other machines only positioned 7 meters from the printer. But we can clearly see a difference in all directions between 20 and 50 Hz, presenting the influence of the copper press, although located 30 meters away from the printer. This problem was solved by inserting Farrat isolation pads made of polyurethane foam below the printer. This highlights the importance of isolating properly heavily We have just observed one potential consequence a poorly isolated machine can have on its environment, but vibration issues can also be problematic for the industrial machinery itself. Let's look at an example of the effect of vibration on productivity using body makers, which are also machines used in the canning industry. Body makers punch the shallow cups obtained from the copper presses through a redrawing die and an ironing ring to transform them into taller cups with a narrower diameter. This comparative study is based on measurements performed on machines running at similar speeds and installed on 2 production lines from a canning factory. All measured body makers from line 1 were connected to their isolated foundations with resilient material in the horizontal and vertical directions. This line was built in 2006 and the model body maker was therefore quite recent. Another set of body makers from line 2 this time were also measured. These machines, installed years before in 1993, were all rigidly coupled to their isolated foundations. This chart presents a comparison of the vibrations measured in the 3 directions X, Y, and Z at the feet of the body makers from line 1 and line 2. It clearly appears that higher level of accelerations were recorded in all axes of line 1 body makers. This can seem curious as these latter are all newer models supposed to generate less vibration, installed on newer isolated foundations. This is actually an illustration of the twofold problem industrial machinery presents in terms of vibration isolation design. To stiffen a connection propagates important vibrations to the surrounding floor and structures affecting nearby machinery and workers, whilst too stiff a connection allows movement within the machine and therefore affects its precision and product quality as a result of misalignments, and damage to the inner lining tool as a consequence of excessive vibrations. In this case, by trying to reduce vibration transmitted to the surroundings by means of resilient material between the body makers and their individual foundations, increased motions have been allowed within the machines themselves. This histogram presents productivity data recorded over 6 months between March 2020 and September 2020 on body makers from lines 1 and line 2. The criteria used here is the overall equipment effectiveness, which is a measure of how well a manufacturing operation is utilized, compared to its full potential during the periods when it is scheduled to run. It identifies the percentage of manufacturing time that is truly productive. For example, an OEE of 100% means that only good parts are produced, 100% quality, at the maximum speed, 100% performance, and without interruption, 100% availability. OEE percentage results highlight the fact that body makers from line 1 present lower productivity with an average OEE of 35%. On the contrary, body makers from line 2 present a higher OEE of 58% collected during these last 6 months. Based on the results from the previous table, a correlation can be made between vibration experience within the machines and how it influences their overall productivity, with availability and performance being lowered and spoilage increased. To summarize, this illustrates the fact that an industrial machine subject to lower In conclusion, we have seen that impact machinery produces shocks, generating huge amounts of energy in a very short period of time. This energy has to be absorbed by means of an interface between the machine and the factory floor to avoid, or at least reduce, the transmission of excessive levels of vibration to the surroundings. A typical way to isolate this type of machine is to insert an anti-vibration system below, made of an inertia block supported by isolators. The measurements performed on different presses have highlighted the very important isolation performance that Farrat anti-vibration systems can provide to the industry, with an overall vibration reduction of 99% from the machine to the floors. The results also show these performances were even improved with the increased machine speeds, which has now become crucial considering the very high cadences and production rate required by the industry. Finally, 2 examples have been presented showing the importance of properly isolated impact machinery. By doing so, effects on nearby sensitive machinery are highly reduced, allowing a freer positioning of the various machines and factories. An appropriate anti-vibration system design is also required, since we have also proven that industrial machinery subject to lower vibration will increase its productivity. Lastly, it is worth mentioning that vibration reduction will also reduce risk to the health and safety of workers usually exposed to high levels of whole-body vibration. As defined by the European Agency for Safety and Health at Work, this type of vibration is transmitted to the whole body and entails risks to the health and safety of workers, in particular lower back morbidity and trauma of the spine. Congratulations! You have now reached the end of this module. For more information on this subject or to discuss an engineering challenge, please do contact us. And remember that reputable manufacturers like Farrat will always be able to discuss design proposals and assist in specifying the right product for the job.